Go ahead.
So this is the public defense of Simon Navia. His thesis is titled "Turbulence-like Behavior of Spot Patterns Mediated by Defects in the Context of the Liquid Crystal Light Bulb Experiment." His jury thesis commission has Dr. Nicolas Bercuren from Exeter, Dr. Stefano Sidori from Nice, and his advisor is Professor Marcel Clerc from the University of Chile. So, Simon, you have 45 minutes for your talk, and after that, we will have time for questions. Okay, so go ahead, you have 45 minutes. You're muted, Simon.
Hello, everyone. Hello, everyone. Do you hear me? I'm sorry. Thanks everyone to be here at my public defense. I'm sorry for the inconvenience that happens today. I have some administrative situations that I need to fix. Well, I already fixed it, but it takes a little long time to be ready. I'm sorry for that. And today I'm going to present my thesis work that is titled Turbulence-like Behavior of Spot Patterns Mediated by Defects in the context of the liquid crystal light bulb experiment. I want to thank my advisor, Professor Marcel, and all the members of the commission present here. Well, from my motivation is the study of the pattern formation in different kind of pattern formation at different length scales. For example, in the some hexagonal disorder patterns in the context of the chloroplasts. And this kind of phenomena repeat in the context of biology in the skin of animals, vegetations, and of course, in the context of fluid dynamics in the clouds that we can observe in the clouds. But in particular, the exact phenomena that is motivate me to study this kind of pattern formation is in the context of the liquid crystal light bulb experiment, when where we can see this complex behavior that we can observe in the experiment, and it has this kind of creation and destruction of different structures. In particular, I study the behavior of these spot patterns. So how can we give an explanation about to this phenomenon that seems to be universal and complex? Well, for this, we need to start in the context of fluid turbulence, that we have this kind of transition that is called the quasi-periodicity route. And we start from a homogeneous state, or in this case, laminar fluid. After that, if we change the Reynolds numbers that corresponds to the order parameter of the system, we can obtain now a spatial bifurcation and the apparition of a spatial mode. After that, we observe the beginning of some oscillations, and after that, we now have the system is now chaotic and have the presence of turbulence. But in the context of fluid turbulence, what is chaotic? Chaotic is when we have some trajectories that they are very close to each other, and these trajectories tend to separate in an exponential way. So in the context of turbulence, we have this kind of chaotic behavior, and also we have the coupling of different scales. This coupling of different scales could be understood through this power spectrum of density spectral, and have this energy cascade in the context of fluid turbulence. That is the meaning of this coupling of different scales. In the context of turbulence, Kolmogorov studied this behavior and discovered that we have this kind of power law in this power spectrum that goes in a way of -5 over 3. But okay, that is fluid turbulence. Now we are interested in the kind of system that we study in the experiment in other kind of turbulence that is called turbulence-like behavior. This turbulence-like behavior, now we have this coupling of different scales, but now we don't have a vector field. We have a scalar field that is evolve. In this case, we can see in the left the model of the Brusulator that tried to model the chemical oscillations, and we have here the Kuramoto-Chibashizky equation, also a very important equation in nonlinear dynamics. In this kind of system, we also have a power law in the power spectrum or the spectral density. And in this example of Kuramoto-Chibashizky, we obtain a exponent of -2 in some interval. Okay. This kind of system, they have a lot of interest in the recent years, and we have a lot of experimental data that support the existence of this kind of behavior. In particular, we can see here an optical system that we can observe phase turbulence, but we also can give different examples in other kind of context. In particular, we have also this kind of power law behavior in stock markets, in chemical turbulence, and we also have in the context in biology some behavior called active turbulence. That here this is not a fluid. This is just some collective behavior of bacteria, and we also have this kind of power law, but with different exponents. But where is the origin of this power law? Some basic model would be, if we start from a statistical mechanic and we only have the interaction between these collisions and very basic interaction, that is only the kinetic energy, we expect to have the distribution of this system could be a Gaussian distribution. But if we now have an interactive system that has a potential dependence through the distance, and if we have some what is the word? Approximations. If we have some approximations, we have now a power. We can obtain a power law behavior in this case. But the important thing here is that the correlations between the system that is in the context of the interactions through the distant interaction could give us the power law behavior. Okay, now in the context of the liquid crystal light bulb experiment, I'm sorry, I just read the chat. It's okay, the presentation? Okay. I'm sorry. Well, from the context of the experiment that we performed, it's important to understand first the liquid crystals. Liquid crystals are a very peculiar molecules that have this anisotropic form, very similar to a grain of rice. And the important thing here is that this kind of molecules have electrical and optical properties. Respect to the electrical properties, they tend to align or anti-align respect electric field. And respect to the optical properties, these kind of molecules have two refractive indexes. The existence of two refractive indexes is called birefringence, and is important in the context of the experiment. Now, here we can see the setup of the experiment, where we have some helium neon laser, and we can change the spatial distribution of this laser through a spatial light modulator. With this artifact, we can create a lot of different spatial spatial distributions. In particular, I study some spatial distributions in 1 and 2 dimensions. But the important thing here is that the light that goes through the liquid crystal here returns to the polarized beam splitter, and after that is behind the liquid crystal. When the light goes behind the liquid crystal, we have this optical feedback. The optical feedback gives us the non-birationals and complex behavior of the experiment, because we also have an electric field in the liquid crystal. So we have two interactions in this experiment. We have first the electric field through a voltage, and optical feedback that is goes that the liquid crystal interact with itself. Well, in particular, I study in the experiment the one-dimensional dynamics of the experiment. For this reason, I create a channel in the context of the experiment using the spatial light modulator, and we can see that I started with a homogeneous state. Now, if we just vary the voltage or the light intensity, not the optical feedback, we can obtain a static pattern. We can see here the static pattern in the bottom of the slide. But after that, now if we change the parameter of the optical feedback that corresponds to the length of the diffraction line, we can obtain now a turbulence-like behavior that corresponds to permanent dynamics. Now we can see here the pattern, how it's moving, and it has a spatial-temporal diagram with oscillations, but also with different scales. These different scales at simple eye is very difficult to see. But if we analyze this kind of profile that has in the experiment, we can see here the emergence of two scales. We have the large scale that corresponds to the critical mode to the experiment, but we have also a small scale that is here. We cannot see at simple eye. Well, for understanding this, well, I already show you in the profile, but we use the Hilbert transform. The Hilbert transforms correspond a convolution of the signal in all the space, in all the space. So we have a value of this Hilbert transform in every point in a space. For this, we use what is called the analytical signal. The analytical signal is defined here through the letter A, and we have in the real part the original signal, but we can add the Hilbert transform through this complex part. So the Hilbert transform in the analytical signal will correspond to the complex part of this analytical signal. Using the Hilbert transform for the data of the experiment, we can analyze the spectral density where we can see a power law behavior and a complex interaction between these two scales. We can see here that this coupling that corresponds to the power law goes through the critical mode to this small scale. We can recover exponent -3 in the envelope, -2 in the phase. And in the context of the time spectral density, we recovered exponents of -2 in general. But we also can understand the behavior through this more elevate power spectrum that we called this the structure factors. So if the power spectrum of spectral density is with exponent of -2, we now can compute the just not with 2. Instead, we use 3, 4, 5, 7, etc. And if we do this, we can show that the autosimilarity of the behavior of the experiment. If the structure factors goes through a line, a linear behavior, we can show that this corresponds to autosimilar behavior and not intermittency. We can do the equivalence of these structure factors with the skewness and kurtosis that corresponds to the higher order statistics of a system. Well, the experiment that we do is okay. We have a good looking results, but we thought that we can do it better. And it's because in the last experiment, we can see a little two-dimensional structures that they are in the channel. And for that, we repeated the experiment, trying to avoid these two-dimensional structures. For that, we changed the aspect ratio of the experiment, and now having a small aspect ratio, we now have a better one-dimensional behavior of the experiment. We can see here the video of the experiment. And if we analyze the profile, we can see that this small scale is clearly seen here in the profile. So it's not just a noise or an error. It's here in the dynamics. And we analyzed the spectral density, and we are now sure that we have this coupling at different scales. And we believe that corresponds to a power law. We now obtain exponents of -2 in general. And for time, we now obtain for the entire field a different exponent. But if we analyze the Hilbert transform, the pseudo phase and the pseudo envelope, we now recover the exponents that we obtained in the last experiment. So well, in conclusion for this experimental part of my work, we characterize this transition. We have a lot of things to compute for this transition, but we have this static pattern. After that, we saw complex oscillations, and after that, we obtained the turbulence-like behavior. The turbulence-like behavior lives in values of this diffraction length of -50 to -70 millimeters of the diffraction length. After that, the pattern seems to be pinned, and we just cannot see the complex dynamic that we see in the last interval. So well, that part was the experiment, but we also trying to give a model for this behavior, a theoretical model. For that, we can start for first principle in the context of the experiment, and trying to model the intensity that reached the liquid crystal through the optical feedback loop. We can write the intensity in this way, but we have now a dynamics in 2 dimensions because the liquid crystal is very it has no a very significant dimensions in the zeta axis. So we now have a behavior only 2-dimensional that corresponds to this angle that is the average of the director, of the 3-dimensional director of the liquid crystal. So this angle theta corresponds to the variable that we are trying to model. And for that, we use a local dissipation equation in the context of the experiment. This equation is nonlinear, it's very complex. We have a root square. It's very difficult to analyze this kind of behavior. For that, we trying to get some approximations. In particular, we can do a perturbation that goes in the center of this theta critical. And now we analyze this perturbation that corresponds to the field U. Also, well, this theta critical corresponds to the point of B-stability and spatial instability. And if we're expanding Taylor this field U and using expansion in the gradient of the intensity that reaches to the optical feedback loop, we can obtain a simplified model that corresponds to the Littr's normal form or a non-birational Turing-Swift-Kohenberg equation. The red part of these equations corresponds to a birational part, and we can define energy or a birational Lyapunov functional to write the dynamics. But the blue part corresponds to a non-birational part, and it has no equivalence in the context of the birational methods. Only in the case of kappa equal to 2c. In this case, it's the only way that we can define a birational for this equation. This equation was derived in the context of the experiment, but it has been found in the context of biology, optics, and chemistry. Just a quotation for all this work. The original birational part that is called the Swift-Kohenberg equations has its origin in Turing notes that he writes this kind of a very similar equation. It's not the same, but it's very similar. And well, trying to study these dynamical properties in 1 dimension of this equation, we can use the Lyapunov spectrum to analyze this behavior that corresponds to the Lyapunov exponent in extended systems. And now we can compute the Lyapunov spectrum. That is a work that did it by Clark and Berkuren. And we can see the transition starting with a static pattern to a spatial temporal chaos that corresponds to the quasi-periodicity root. And well, that is a dynamical analysis. What happens with the statistical properties of this model in 1 dimension? Well, we perform several numerical simulations to this model, and we computed the spectral density of this model. In the image C, we can see the spectral density that we have of this model, and that's it. We have something that is decaying, but it has several modes that corresponds to oscillations and spatial modes. So this is the spectral density. But can we obtain a more clear behavior of the complex behavior that we observe in this pattern, in the spatial temporal diagram? Well, for that, we can separate the dynamics. For that, we separated in oscillation part and a chaotic part. For that, we defined this difference between two very similar fields, U fields, and in the right image, what we can see is the difference between these two parts of these two fields that they are very similar. If we do that, now we computed the spectral densities, and we can see using the Hilbert transform a better description without these all kind of oscillations and peaks. We can obtain something that seems to be a power law, and for the phase we obtain an exponent of -2 and very similar to -2, between -2 and -3 for the amplitude, for the pseudo amplitude. Also, we tried another way to filter this kind of oscillations, and we tried with analogical filters that correspond with. We tried several methods, but here's only the more basic filter that we use. That corresponds to the Butterworth filter, and we obtain exponents of -2, a very clear exponent of -2. We also tried a more complex simulation of the phenomenon in one dimension. We simulate those numerical simulations of the entire channel in a two-dimensional array. And we can see here the temporal evolution, that we can see some kind of defects that are creating and destroying. But now we have this spectral density. Maybe it's not a linear behavior in the spectral density, but the more basic possibility to be is like a power law. So we separate two regimes that we observe here. Well, it's like this was just a try that we're trying to model the system. So another possibility is trying to study the system with a prototype models for complex behavior in patterns. And we have here the very famous equation that corresponds to the complex Invert-Landau equation. This model describes the behavior near an oscillatory instability. But the important thing here is that it's only in the case that this oscillatory instability occurs in the context of a homogeneous solution. So this is the equation. We have two parameters, alpha and beta, and we have here the phase diagram that corresponds to in one dimension. We can see phase turbulence, different complex behavior, phase turbulence, amplitude turbulence, or mediated by defects, and spatio-temporal intermittency. We analyze statistically the behavior of all of these complex behaviors in the context of the complex Landau equation, and we can see the spectral density of phase turbulence in this case. Well, maybe here is not very clear the exponent, and we try to do it in semi-log to be sure that corresponds to a power law or the exponential. Maybe it's not very clear in this plot, but we're trying to do several analysis in the future. We have here intermittency when it's more clear that we have here in this part exponent of -5, and for defect turbulence we also have an exponent of -5. So well, that corresponds to Ginzburg-Landau equation that has several differences with the experiment that we performed. And for that, we are trying to search for another model. In particular, the complex Simon-Landau equation, I say that it's only valid for when we have an oscillatory instability but with an homogeneous solution. Now, we're trying to explore with models that goes not with a homogeneous solution. Instead, we have a periodic solution in spatial and not in time. And this spatial pattern has this oscillatory instability. In this case, it's more complex. We have now the phase of this pattern survives as a Goldstone mode, and we have now an equation that is very similar to the complex simul lambda equation, but has a coupling term with the phase of the original spatial pattern. And we also have another equation that is the evolution of this spatial phase of the pattern. And now we have a coupled system of differential equations. Well, to study this is very new, and to study this kind of system, we start with a coupling of zero, no coupling at all. So now we have only the amplitude equation. In this case, we use the parameters of alpha beta correspond to defect turbulence to study this. I only did the analysis with this kind of parameters in the region of defect turbulence. For that, we can see in the phase equation that we have, well, for delta equal to 0, we have just something very similar to defect turbulence. But if we change the parameter delta negative or delta positive, we now have some patch dynamics that is like domain dynamics between this phase. We found several new states in the context of this new model, that the Coulette-Jost model, and they are it's like something like a combination between the turbulence and fake turbulence, intermittency, etc. They are very interesting, but they are not very similar to what we observe in the context of the experiment. In this case, for the construction of the original signal U, we use a test function that corresponds to a pattern, a cosine function, plus the behavior of the amplitude and the phase of the equation. Well, we have reconstructed here the spectral density and observed this kind of behavior. Maybe it's not very clear that we have the power law, but we're trying to do several methods to try to figure out what's happening. Here we have another parameters of the same model, and we observe here something that is more similar to what we observed. Also, it's not the best this model maybe. Also, I did some results in 2 dimensions in the part of the experiment and in the parts of the theory in the context of the Lipschitz normal form. In the context of the experimental results, we're trying to figure out what is the transition in 2 dimensions, and we start with a homogeneous solution. After that, we saw something that is very similar to front dynamics between 2 states. And after that, we observed the turbulence-like behavior. We're trying to improve this kind of experimental results because in the case of the turbulence-like behavior that we observe here, we observe some mix between spot patterns and labyrinth patterns. Maybe we can do it better in the future with just only the spot patterns. But we analyze the spectral density of this turbulence-like behavior in the context of the experiment, and we obtain this kind of curves. I corrected from the last presentation the validity of the line here, and maybe it's more small the interval that is valid. But we're also trying to figure out in a semi-log spectral density, and maybe it's not a power law and it's exponential. Both cases are complex, and we are trying to do more analysis in the future for these cases. In the context of the theory of the equation that we use in 2 dimensions, we now have the operators in 2 dimensions that corresponds to the Laplacian and double Laplacian. And we start with a pattern, with the spot pattern, only for the variational parameters. And after that we create this spot pattern, we can now vary the non-variational parameters correspond to kappa and C. If we just vary kappa parameter, we obtain more defects, and these defects tends to be bigger, but the characteristic length of the patterns decrease at the same time. But the problem here is with just varying kappa, we didn't observe dynamics in the system. Now, if we vary C parameter with a value of kappa fixed, we observe the emerge of a hexagonal pattern, and after that we observed automatically the emergence of turbulence-like behavior. For the hexagons, where we are trying to figure out if they are hexagons or not, and we compute the Fourier transform in 2 dimensions, and it's clear that it has these 6 spatial modes. So it's really some kind of hexagonal pattern. Well, here is the simulations, the numerical simulation of the turbulence-like behavior that we observe for this parameter that we have here in the slide. And we observe here something very similar to what we observe in the experiment. But the problem here is like we need a lot more study of the transition because it's not the same that we observe in the experiment. Also, we can see the complexity of the spatial-temporal diagram, but the results that we have in the context of the theory of the numerical simulations is very different to the exponents -4 that we observe in the experiment. So we are trying to figure out what is how will this difference can occur between the experiment and the numerical simulations. Also, in the context of time, we obtain an exponent of minus 0.5. So it's different to the exponent of -2 that we obtain in the context of the experiment. So, well, for the conclusions, the most important thing in the experiment was the discovery of these power law behaviors in the spectral densities, that they are coupling 2 scales. These 2 scales was found to be the critical scale and a more small scale that they are coupling. So this power law corresponds to a coupling of 2 scales. Well, I want to add to this part of the conclusion some comment that Professor Nicolas Verkuren told me in his comments, that it was really interesting and I tried to thought about it, that what is the advantage of this kind of analysis compared to the Lyapunov spectrum? Well, my answer to that is that there are different phases of the same phenomenon. In the case of the Lyapunov spectrum, we only measure the spatio-temporal chaos of the system. But this spatial chaos can be several cases. For example, in the context of Landau, we have spatial-temporal chaos in phase turbulence, in depth turbulence, and intermittency. But we don't know just with the Lyapunov spectrum what kind of behavior it is. So this kind of statistical analysis could give us an answer about what is the color of the hair of this spatial-temporal chaos. So in this case, we can observe the creation and destruction of defects. So we are very sure about the defect turbulence of this phenomenon. We also analyze the transition experimentally, and we have a further analysis to do in the future But we have some very complex oscillations, and after that, we observe the turbulence-like behavior. In the case of the numerical simulations, do it with the Lifshitz normal form, we found this spectral density that corresponds to the difference only correspond to the complex chaotic part of the system, and we now recover very similar exponents and behavior compared to the experiment. In the part of the two-dimensional part of my thesis work, we analyzed the transition that go beyond here, and we conclude that is completely different compared to the one-dimensional case than when we have in the theory the quasi-periodicity root. In 2 dimensions, we have the hexagons, and these hexagons destroys, and we get the turbulence-like behavior immediately. So it's very interesting, and we're trying to figure out what is the bifurcations that goes here. Thank you very much for your attention and your time to read my thesis and give me several comments that they are very, very interesting all of that. Thank you very much.
Thanks, Simon. So we are going to start with a round of questions. We're going to start with Professor, Dr. Stefania Residori. Can you go first, Stefania?
Thank you, Claudio. Thanks for the invitation to this jury thesis. First of all, I would like to congratulate Simon for your work, which provides us such a detailed study on turbulence-like behavior in a nonlinear optical experiment, and especially because you took the challenge of deriving this power loss, which is still sometimes a controversial subject in the domain of nonlinear optics. I think you have the merit to have really went into the details of this, and you checked the different type of model, one-dimensional, two-dimensional, and really you did a big amount of work in this domain. So I would like to congratulate for the presentation, because it is clear, and really, even so you have so many different subjects, and it is clear, well organized. Okay, so and pedagogical also. You were very well explaining the context and the challenges each time. So I would like to start with a simple question, sort of technical. When you show sometimes the profile of the intensity and the profile of the pseudo envelope, and we see that they are very close, there is not so big difference between the two. And so my question is, what is the information which is brought forth by this here, for instance? What the pseudo envelope tell us more than the intensity profile itself?
So we're going to wait a little bit for this, Simon.
Okay. Do you hear me? Yeah. So is that because
yes, now, yes.
we have the two computers, we have interference. So okay, I'm sorry.
I see. I didn't understand well.
Well,
Okay.
it's a very good question. So we're gonna get the envelope of the amplitude, get an equivalence to the slow dynamics and the original field to the fast dynamics. In the context of the experiment, the difference in the profile is very no, it's not very much because the original field, the intensity of light, could be only the value of 0. So if we have a pattern that has their behavior in the negative part also, that we can see in the theory, the difference is more bigger. But yeah, exactly. But the more important part is that when we do the evolution of this pattern, in that case is that we can see more accurately the difference between the pseudo envelope and the intensity, because the dynamics of the pseudo envelope is the slow dynamics compared to the dynamics of the intensity that is fast dynamics. That's my question. That's my answer. That's my answer.
Okay, I see. So the information is more on the dynamical behavior than on if it's
exactly.
Okay, I see. Okay. And then I would like to ask you again if you can just discuss briefly this relation between spatio-temporal chaos and turbulence. So why this behavior that we see here, you qualified of turbulence or turbulent-like behavior instead of spatio-temporal chaos?
Well, they are not, we cannot like, it's not just one or another. They cannot coexist. In particular, in this context, the spatial-temporal behavior, spatial-temporal chaos behavior of the experiment just get computed. And we know that it's spatial-temporal chaotic. But the turbulence-like behaviors corresponds to the coupling of different scales. In the context of fluid turbulence, we have several scales and we have several decades. But in the context of turbulence-like behavior, the structures and the critical length of the pattern is fixed. So we just have, for this experiment, the coupling of the critical length of the pattern and this small scale. And that corresponds to the coupling that we observe in the power law. But I want to get the point that they are not, they can coexist. It's not just we have only spatial-temporal chaos or turbulence-like behavior. Spatial-temporal chaos could be turbulence-like behavior or could be intermittency. It's like what Professor Marcel gave me a very nice example that if you have hair, that corresponds to the spatial-temporal chaos, but your hair could be brown or could be black or could be yellow. It's like another property of the system. They are not opposite. Okay. Okay,
so you mean there is a sort of coherent frame in which we can say spatial-temporal chaos, but exhibit more turbulent-like behavior if we have several scales and something like that.
Yeah,
okay, nice explanation.
Nice. The spatial-temporal chaos corresponds to a dynamical property. The turbulence-like behavior is a statistical property of the system.
Okay. I think it's a nice way of seeing things. Okay. Then at the beginning you have shown several examples of systems that exhibit turbulent or turbulent-like behavior. And then you focus on the liquid crystal live valve experiment. And you think that liquid crystal media are particularly suitable to observe turbulent like or spatio-temporal chaotic behavior? So for some reasons, or other type of nonlinear optical media could have exhibited similar behavior? Which is your feeling with that?
Well, if the question is like is solely a property of the liquid crystal systems, I don't think so. I think the turbulence light behavior is a very robust phenomena that is seen in many different contexts. So I think it's like a more open questions like what are the ingredients that we can have in the dynamical system that could arise to turbulence light behavior? It seems like we need chaos, we need a special temporal chaos, but we need a nonlinear model. So, for example, in the Kuramoto-Chirexis equation, has this kind of phase turbulence, but in another kind of context, the stock markets, for example, they are not at all similar to the Kuramoto-Chirexis equation, but they also have this kind of turbulence-like behavior. So I think they are not only in the context of liquid crystal, they are very universal behavior, and they correspond to a non-equilibrium phenomena that we can measure in different contexts, not only in liquid crystals.
Yeah, sure. Yeah, sure. But for instance, so the power law that you have derived in this particular kind of experiment, do you think they depends on the fact that you have the liquid crystal medium, that you have the optical feedback of both? What do you think? What do you expect? Do you expect that a similar experiment with maybe not the liquid crystal, but another medium could exhibit the same power laws or different? What do you expect?
Yeah, well, I think it's not like in a, we need the liquid crystal like the base to construct this kind of dynamical system. Like, I don't think the liquid crystal is the main ingredient to this turbulent light behavior. I think the main ingredient in this kind of experiment is the optical feedback loop, that is the main ingredient to these non-rational terms in the context of the theory. So I think the main ingredient here to obtain this kind of turbulence light behavior and the exponents that we observe is the optical feedback loop.
I agree with that, because this is giving you this non-variational part of the Ginzburg-Landau equation. Yes, sure. Okay, so let me ask last question maybe. So in this type of experiment with feedback on linear optical medium, there has been in the last time a lot of observation of optical rock waves. These big events appear rarely, no? Which exhibit specific statistical distribution and so on. Do you see a link with the turbulence-like behavior, with maybe the precursor of rock waves, or do you think there exists a link between the two phenomena of rock waves and turbulence?
Well, with rock waves, do you mean like extreme events? Yeah, extreme events. Yeah.
Yes.
Yeah, I think they are linked because the extreme events corresponds to the tails of the distributions tends to be more significant compared to the rest of the distribution. So I think that this kind of power loss that we found in the turbulence light behavior could be maybe a correction to this a Gaussian distribution. So I think in particular in the turbulence light behavior, we can also observe this kind of extreme events, but to be only a system of extreme events, maybe we need another ingredient or different parameters to be only in the context of extreme events, because in the context of the turbulence like behavior that we observe, we just saw this kind of dynamics, permanent dynamics, but we are not very interested about the values of these patterns that we observe. So maybe if we do the analysis of the distribution of the intensities that we observe in the context of the turbulence-like behavior, we can also obtain extreme events. It's very interesting. I think it's something that could be interesting to analyze the distribution of the extreme events in the context of the turbulence-like behavior that we observe.
Yes,
Thanks for your comment. I think it's a very good suggestion about the something.
I think so. I think it would be worth exploring of this. Yes. Okay. And then, yes, what else? About the two-dimensional experiment, you have shown hexagons at some point. That is hexagons in the far field. Could you relate this to from numerics to experiment? These hexagons that you do.
Yeah, it's something that we want to do because the experiments that we perform in 2 dimensions, maybe they were not the better, but we didn't observe. That is something that is very curious for me. Like, we didn't observe the hexagon pattern in the 2 dimensions array that we did in the experiment. We just observed this kind of front dynamics between two vista states. So we are now trying to observe this kind of transition that we already did in the numerical simulations. But what are the parameters in the experiment correspond to the hexagonal pattern? I think it's something that we are not already have the answer, because we need not only the hexagonal pattern, we need the hexagonal pattern that give arrays to the turbulence-like behavior. So yes. We
Yes,
just
you could you could have sort of front dynamics between patches of hexagons differently oriented or something like that, maybe. That would be nice to see.
Yeah, I agree.
Okay, Simon, thank you. That's enough for me.
Thank you very much for your questions.
Thank you.
Thank you, Stefania. Now we go to the question of Dr. Nicolas Verkuren. Nicolas, go ahead.
Thank you, Claudio. Well, first of all, I really enjoy reading your thesis and this presentation as well. It's very clear to me that there were significant improvement between the first version and this one. Can you hear me okay? Yeah. Okay. Yeah, so I don't really have any concerns or anything like that. So my questions are more about scientific curiosity than anything else. Okay, so let's start by the questions that are kind of with the more technical. So can we go to the part where you put the straight line or the quadratic line? I don't know how this is gonna work. Ah, okay, he's gonna bring the laptop. That's a good idea.
I'm sorry. The linear. Yeah, put there. Okay.
Okay.
It's like here.
No, it's where you have where you put the quadratic line.
Quadratic, what?
Yeah, you said that you fixed that.
It's like in 1-dimensional or 2-dimensional?
I can't remember. I think it's 1-dimensional. After it's where you identify the region we're seeing. Yes, or I think next one as well, maybe. Yeah, this one. So you said that you improved this. Can you elaborate on that, please? So in particular, I want to know, what's your criteria to choose the interval of k? What was the change in it?
Yeah, well, maybe I could agree that maybe the power law here or the line is in the more behind the not in the part that we I put it. Like, maybe it says in another part of the line. I could agree with that. So I did the semi-log representation of this, like to be sure that it's exponential or another thing that could be complex also. And well, maybe the power law is not in the part that correspond, but I try to get the same result that got Kuramoto in the context of meaningful Landau equation. In the part of free structures, when the amplitude equation is just not only valid and we have only the dynamics of the phase. And we know it's very well known that this exponent is -2. So maybe it's not very correct. I could agree that I try to get this -2 in the plot. Maybe we need more statistic in this case, or the parameters are not well fitted.
Okay, that's fine. But then if you show this picture and you're saying, look, it can be -1.9 plus -0.1, that you're doing that by forcing yourself to look into an interval of k, right? Which means
Yeah.
that in some sense, that's the interval of k that matters. Do you have any reason to believe that why that should be the case? In the case of Kuramoto, I imagine it was the same.
Well, why I choose this interval? That is the question, yeah?
I mean, you choose the interval because it works there, but do you expect to have this an interval of k's, right? So probably there is where something important happens. Do you have any thoughts on that?
Well, I think that we are just dominated by the after. Well, in the context of the interval, we need to view the plot after the critical length. That is very trivial. That the complex behavior is after the critical length. In this case, the critical length is like here. So after that, we just say that after the critical length, all of this is like a power law behavior. But it's not very clear if we put a power law there just after the critical length. It's not fit well.
Mm-hmm.
So
yeah, no, that's fine. Then my second question is in the 2D case, when you look at the non-variational TSH equation, there's a part where you say that the kappa value change the wavelength of the pattern, right? If I understood correctly. In the 2D case.
Yeah, I understand.
Yeah. Yeah. So what happened here is that the distance between between dots is smaller. Is that correct, or larger? What's happening? Just to understand this part.
Well, the spatial length of the domain is fixed. So we in the same length of spatial lengths, we observe the increase in the number of dots. So this increase in the number of dots I interpret like we can be sure the characteristic length of these spots, and they tend to decrease and create more and more spots, and I think it's very clear in the image that we have a lot of more dots in the C image than in the A image.
Okay, yeah, I just wanted to clarify that. I didn't understand very well when I said it. Okay, and now more general questions for you. So my first question, I guess, in a more general context would be, there's some part of your narrative that I find hard to follow. So first you talk about this experiment, and I understand why the experiment is interesting, etc. And then the natural model that appears from there is this Lifshitz model. And then there is this Yoast model. So why the Yoast model? What is the thing that you were expecting to find in the Lifshitz model that you didn't? And then you thought, well, let's have a look at the Yoast model.
Well, it's always interesting to get a description using only the amplitude. Like, for example, in useful lambda equation, we don't have access to the U field that corresponds to the entire field. And we just have information about the amplitude. We can reconstruct the original U field using the amplitude and the phase of useful lambda equation. We can agree with that. But I think that is the answer. Like, it's so interesting to find an amplitude equation for our phenomena, and the change between the Lipschitz normal forms, that is an equation for the U field, and an equation for an amplitude. Like, what is the transition between these two equations? And I think that's we are very sure that it's not complex Gimbel lambda equation. That is not the equivalence to the Lipschitz normal form. So with Professor Macedo, we're trying to question about what could be the amplitude equation of this phenomena that describe the Lipschitz normal form. And we answer it by the Coullet-Yoast equation. Because in the experiment, also in the theory, when we do the transition through the turbulence-like behavior or spatial temporal chaos, we start always with a static pattern. We don't have the homogeneous state. So we believed that that is a main ingredient to the construction of an amplitude equation of this kind of phenomenon. And the Coullet-Yoast equation has this ingredient, and it's in its birth. So the Coullet-Yoast equation would be the amplitude equation of the Lipschitz normal form, but we don't know why it doesn't work well. We believe that this Coullet-Yoast equation that corresponds to the amplitude equation of the Lipschitz normal forms would be the same results, but it doesn't. So that's a good question. Why?
Okay, and then that's great that you say that, because that takes me to my last question. So if I understand well, this Coullet-Yoast equation is built from the symmetries of the system, right? And in theory, you could derive it from another equation. And then you find out that it doesn't work. So that means that you propose these two models, these two generic models, to try to capture what you're looking at in the experiment. And then you say that you're not capturing some part of it. What do you think is missing that is in the experiment? And if you have another 2 years, a year to do another master's, what do you think should be the next thing to look at to try to capture these behaviors in the experiment?
Trying to capture, like, in the theory or in the experiment? In the experiment.
Well, you said that what you observe in the Coullet equation doesn't work, doesn't look like what you observe in the experiment. What do you think is missing if you need to do another attempt to come up with a model? If you have to amend this Coullet-Yoast equation, for example, what do you think is missing there?
Well, it's a very deep question, but I think the Coullet-Yoast equation, maybe it's like it's too generic, like, because its origins, like as you say, it's the origin of this Coullet-Jost model is all in symmetries. We don't have information about the mechanisms that the experiment is performed. So maybe just with symmetries, we don't have the entire information about the experiment. I think the typical way that I imagine is like trying to model in terms of amplitude the optical feedback loop in the context of the Coullet-Jost model. Maybe it gives another information, adding another information compared only with the symmetries that has the Coullet-Jost model.
Okay, that's good. I don't really have any more questions, Claudio. So thank you very much, Simon.
Thank you very much, Nicolas.
Thanks, Nicolas. So I think now it's my turn for questions. I like Nico, I post almost all my questions in the private your private presentation. So I just have some issues and questions about, I think, the interpretation of what you said. For instance, you discussed a little bit about the transition from spatiotemporal chaos to turbulence, and you talked about the quasi-periodicity route to turbulence that was already tested in some systems. So my issue is, what type of transition do you think, or do you measure, or you noticed when you studied your two models, either the Jost-Coullet model or the more complex, already tested Suifo-Emberg-1? So what type of transition from one state to the other, if one state being, say, spatiotemporal chaos and the other one being turbulence?
Well, in the context of the Lipschitz normal formal, including Suifo-Emberg equation, that number the transition is very understood, that we have in one-dimensional, we have the quasi-periodic route, and in two-dimensional, that is something that I was working, that we have this hexagonal, and after this hexagonal pattern, we have the turbulence-like behavior. It's not very understood in two dimensions, the transition to this turbulence-like state. But in the context of the Coullet-Jost equation, we did improve the transition. That is it's a very good question, because we just started with a state that corresponds just a defect turbulence in the parameters of defect turbulence in the context of Ginzburg-Landau equation. If you ask me, I think the transition could be the same, because it's the same kind of phenomena, but it needs to be tested. I agree with that.
So just to be clear, so did you test, or did you measure, or do you have some sort of information of how does the system in two dimensions become, or goes from one sort of spatiotemporal chaotic state to a turbulence-like state? Did you measure that? Do you have any information about that, or you're just trying to apply what you already know in one dimension?
No, we try to explore the parameter space that the transition to chaos in two dimensions. We did that work, but we need to analyze better through several simulations. That we need to do a lot of simulations to be sure what are the parameters and what is the phase diagram of in the plane of kappa c, the non-rational terms, in two dimensions. Because I also observe a lot of different states in two dimensions. There is not only hexagons, there is a lot more. But so in one dimension, we have just a line. with only the C parameter. When we have a static pattern, an oscillating pattern, we now observe non-measurable oscillations with a very complex oscillations, and after that we have the spatial temporal chaos. But in 2 dimensions, the role of kappa parameter is very significant. So we just not have a one-dimensional line. We have a phase diagram in 2 dimensions. So just what I show you here is like a minimal part of the entire dynamics in 2 dimensions. I think maybe the hexagons is not the only way, and there could be another way to obtain the turbulence light behavior or spatial temporal chaos.
So just to be clear, so you haven't tested you haven't measured really the way the 2-dimensional state goes from a spatiotemporal chaotic state to a turbulence-like one. You just observed something that changed, but you don't really characterize the way it goes from one state to the other.
Exactly. We need to measure I think we need to measure the eigenvalues that corresponds to the modes of the hexagonal states. We need to perform that analysis to be sure about the transition. That's correct.
Okay, I think that was actually my question. If you noticed, if you know what type of tools to use in order to characterize how you go from one to the other one. Okay.
We need to measure like the values of the bifurcation. We need to measure about this, but we didn't did it like right now. But we want to do it like in 2 dimensions. Yeah.
Okay. And the other one is, I think it follows the question of Nicolas's. What's the meaning of this inertial range you see in your different plots? So you have an inertial range. That means you have a window of k vectors or frequencies where you think you have this sort of scale invariant or power law behavior. And what is the meaning of that range? Can you say something about the relationship between a certain range you measure and the dynamics of your experiment?
Yeah, well, this kind of inertial interval that we have in the context of the experiment is very clear that has the meaning of coupling of these two scales that I talked about. But I could agree that maybe well, we always can fit a line in some interval. It's always the most simple way to get a fit. But I know that we need to get a meaning of this, and maybe it's not linear. I could agree with that. It's complex anyway. We could have a exponential behavior, and it could be complex, but I think it gives you information about maybe we need another statistical tools, but it gives information about the statistical distribution about the system. When, for example, in the context of the structure factors, the skewness on the more higher terms give us another additional information about the system. Well, here this power law could give us information about the distribution of the system, I think.
Yeah, I agree with you actually. I think that more tools need to be developed. But I think also that it can be highly complex and highly interesting to study systems that don't really present power law behaviors, and that's a very important and I think profound discovery you made, that complexity it's not really related just to scale invariant laws. They can actually develop in very well fixed scales, and you can have lots and lots of complexity within them. So I think that's an important point. And lastly, I would like to ask you about what you think experimentally one should do to test or to probe the two models you presented. So you have two models that describe certain dynamics, and you try to fit them onto the experimental setups. If you can do it backwards, what type of experiment would you do in order to test that your models are correctly describe the dynamics or incorrectly describe the dynamics?
Well, in the context of for example, the Lipschitz normal form, we expect the validity of this model only in the vicinity of this Lipschitz point. So maybe this model, we can test the validity of this model, get us very far away from this Lipschitz point. And I think the most interesting feature of this Coulomb-Jost model is like it's not only valid in the Lipschitz point; it has validity in any point. So maybe we can create some parameters in the experiment that we are far away from the Lipschitz point, and in that case, maybe the Coulomb-Jost model could be better. Right? But it seems like in the present, like it seems like that's not the case, and we don't know why. I'm sorry, but we don't know why. But it seems like the Lipschitz normal form it's a good agreement, not only near to the Lipschitz points, and very far away. We also I have read a lot about some modifications in the Coulomb-Jost model, but they are more complex and they have a lot of more parameters. So we have now a discussion like, is a better option have a better model, but they have a lot more parameters. Maybe it's not worth. Right? The validity of a model is not only that we observe but we can see in experiment. Also, the numbers parameters that we need to fit this model is important, I think. In the case of the Lipschitz normal form, we just have two parameters of the non-variational terms. In the case of Coulomb-Jost model, we have 4 or 5, and the modifications of Coulomb-Jost model have 7 parameters. So that part of the discussion, I think, is important also.
Okay. Yeah, I'm confident that you really understand what you did. I really like your work. So I have no further questions. I give the word to Marcel now.
Okay, so first of all, I want to congratulate to Simon because he has done a very nice work. I mean, an integral work in the sense that he do experiment with another student, of course, more specialized in experiment. He do a lot of analytical analysis. I mean, numerical. More the majority of the work was numerical, but he do a lot of work. So first of all, I want to thank for that, and the result I'm very happy. And first, I want to do some thinking about maybe the question that Stefania asked about the chaos and turbulence like and the difference. And maybe I come back to maybe the very, very, very early problem of chaos was done by Maxwell. Maxwell studied the dynamic of a gas. And Maxwell, when he tried to study a gas, he tried to take different particles. For instance, he tried to study the collision of 2 or 3 particles. And he discovered that it's not possible to he said precisely what is the chaos is. He said that if you do a small modification, the result of the collision is difficult to predict. But why this is interesting? Because if you take a gas, if you take a very microscopic part of a gas, the system is chaotically, okay? If you increase your gas, the system is spatiotemporal chaotically. So because it's extensive, more bigger the system is the, oops. Okay, so the system is more bigger, the dimension, sorry for that, I have a, so the system is more bigger, so the system is spatiotemporal chaotic. However, if you try to compute the statistical behavior of the system, for instance, we know a good approximation is a white noise. So if you compute the Fourier transform, it's flat, no power law. If you compute the velocity, you found Gaussian. So the question is, when we have complex dynamics, what we observe, okay, chaos means sensitive to the initial condition. But spectrum density, for instance, means some rules or some equilibria that the system established. So apparently different systems have different power law or different power density or different structure. And the question is open. I mean, any system far from the equilibria apparently exhibit very interesting behavior. The question is which are universal or not, we don't know. Apparently in the pattern forming system, this kind of pseudo amplitude equation allow us to say maybe it's universal power 2 or power 5. Some power apparently are more recurrence as consequence maybe of the filters that we use to compute. But all the work of Simon is framed in this kind of question of we have complexity and we try to understand the complexity. Okay, so but I try to emphasize that, okay, there is a lot of work in fluid dynamics, but it's not the only point of view. I mean, all these kind of patterns can exhibit very, very interesting and complex dynamics. And in this very simple experiment, we discovered that even in 1D, we observe complex dynamic. Even in 2D, okay, Simon for the moment don't work or don't show too much in this direction, but we have more and more complexity, and we try to understand more or less. This is the point. So the question for Simon is more or less if I try to see your results. So the question is, in your opinion, what we learn from your thesis?
Well, we learned that this kind of spatio-temporal patterns that we study, they have well, the power law, the exponential law that we found is always due to the coupling of the different scales. That is what I observed in one-dimensional case. Well, in general, I think the behavior of this turbulence-like behavior is always related to I don't know. Well, in the experiment, it's always related to the dynamics of the defects, but not only the defects. That is something that we figured out in the path. Like we start thinking that the defects are very important, but in reality, maybe they are not so important. And we observe this kind of dynamics that emerge not only with the defects, and we have this coupling of the different scales.
Okay, very good. Okay, so my last question is, okay, which is your next step, or which is your advice to we move in which direction? What do you think about it?
Well, I want to study now what is the true transition in 2 dimensions, and I like to study to get a better statistical description that we already have in the context in 2 dimensions, that maybe start using more sophisticated techniques and methods. I think that's the best way. It's the best way.
Okay, Claudio, for me, it's okay. I want to say the last again, I congratulate to Simon because really do a very hard work. So I'm very happy for that. and in a very, it's not in a short time, but more or less in a short time compared to my other students. So very good in that situation. Okay, Claude.
Okay, thanks, Marcel. So, Simon, now we're going to ask you to leave the actual room because we have to deliberate.
Okay, but Claude, let me wait 1 second. Stop to
Record, yeah.
Maybe.
Okay.
Okay, now it's okay.
So, Simon, your thesis commission has discussed your presentation and your discuss also your manuscript, and we've agreed to give you the maximum degree as a master student, both in your presentation and on your master's degree. Regarding that, you have the requirements for that. Your degree, your notes have to be larger than 5.5. So congratulations, you've achieved your goal. You're a master. You have a master degree, and the commission is very pleased with your presentation.
Thank you very much.
Okay.
So I expect that in another opportunity we can open this for Simon, but it's not. We cannot because here is forbidden to drink alcohol. But maybe outside to the university we can open this.
Yeah, and we should delete that part from the presentation also.
Okay, I don't know if anyone want to say something to Simon to congratulate. I don't know if Simon or no, sorry, Stefania or Nicola want to say something.
Yes, congratulations, Simon. Very nice work. We enjoyed a lot your presentation. I hope you continue like this for your PhD and your future career as a scientist.
Thank you very much. Just fine.
Well, yeah, congratulations again. I think I didn't have any doubts at any point of the quality of your work, in survey your thesis, and best of luck living in Germany. Yeah.
I'm very excited because I will continue my work in extended system. So I'm very happy to the place that I will do my PhD.
Very good. Okay, so I want to thank everyone, and of course, I don't know if Claudio would like to say more, or it's okay, Claudio. If you are...
No, for me, it's okay. I think we praised Simon, his work, and we're just very happy for him. And hopefully he's going to be having his continuation in Germany.
Thank you.
Okay. Okay, thank you everyone to be part of this commission. Thank you again for that and for all the work. And thank you, Simon. Anyway, you was done a very nice work. Very nice.
Thanks, Professor.
Okay.
Okay.
Bye. See you. Bye,
Thank
Stefania.
you.